All right, and finally we have number 3, which I promised you would be Kirchhoff's loop rule. All right, that's what that's saying is, let's say I have a circuit. I'll look at a simple one here and a complex one in the example. I think you'll see what I'm saying here a little bit better. Say I have a circuit like this, and I'll put it to ground there, and I have my voltage here, I have my battery here, and then I have my resistors here. Well, because this is V equals 0, we can see that if I go up to this voltage, let's say it's 9 volts, if each one of these is the same, I will go from 9 volts to 3 or to 6 volts to 3 volts and back to 0, right? We always have to go around to back to the same point. And remember, that's because voltage is like height. Remember, this is the energy of the electron, the voltage E, right? The energy of the electron is Q times V at whatever point you are in the circuit, right? So that energy comes from the battery, and so when you get back down to the bottom here, you've used up all that energy. Just like if you're on a water slide, when you climb up the ladder, right, you add potential energy, and when you go down the water slide, you eventually come back down to the ground, right? So you can think of the potential like the height. So you go to your maximum height, then you go to 2h over 3 here, and then you go to h over 3 here, and then you go back down to 0 here. And so each one of these different slides on your water slide, each one of these different parts of your water slide, is like going down one of these resistors. So each point in your circuit has the same potential, or each, no matter how you got there, right? Even if you have a much more complicated way of getting there, right? If, you know, up the top of the water slide there's a door, and you could go through that door and then up some stairs and then down an elevator and then up some more stairs. To get back to this point, you still end up at 0, right? Same thing in a circuit. Doesn't matter how complicated the series of resistors is, when you get back to the same point, you're still at the same voltage. Just like here, no matter how you get there, you're always at the same height when you get there, right? So, and it doesn't matter, you know, how high you've had to go up and how far down you've had to go. You could go to the 10th floor of a building and then down to the 6th sub-basement or whatever. I've never seen a 6th sub-basement except for in the movies. Usually, if they have a 6th sub-basement in the movies, there's something creepy going on there. All right, so don't go there. And that's more or less all that it is. There's nothing more to this loop rule. It's just then you have to apply it, and the application will be the example. And like I said, that's going to be the big example. The voltage at any point in a circuit is independent of path. That's also something we found with conservative force, the energy from a conservative force, right? If the energy is independent of path, then the force is conservative. This is just sort of reiterating that the electric field is conservative. What does that mean? That means any full loop through a circuit, returns to the same position, or to the same, not position, that's for water slides. Okay, and basically up a battery is positive, and following the current in through a resistor is negative. We've already done that in our earlier investigations, right? Up 9 volts, down 1/3 of, or 3 volts, down 3 volts, down 3 volts, back to V equals 0. So these are really just the same rules that we've been following the last, let's say, 2 lectures. So nothing really new in that, all right? But you have to really keep track of while you're doing the rule, all right? So I'll do a complicated example that will put both of Kirchhoff's rules together. I hope it illustrates something. It should illustrate something, but hopefully you can look at that. It's hard to see the importance of these things until you actually get to the big algebra stuff, because otherwise it's really just sort of banal. It's what we just talked about previously. It's up and down, back to where you started. But this becomes really, really important when you have a complicated circuit and you want to make sure that nothing's going the wrong way, right? So all of a sudden, these 2 banal rules, right? The previous rule was just what goes in must come out. Those 2 things together really let you analyze a circuit and what's going to happen in a circuit, all right? Okay, bye now.